Okay, in this video, it's not going to be very long. This is just to kind of explain to you how cations and anions, or the conjugates that have the cations and anions, affect pH. So an anion that is a conjugate base of a strong acid doesn't affect the pH at all. So if you have a strong acid like HCl, the first deprotonation of sulfuric acid, these strong acids, the anions of them do not affect the pH. And that's because when the strong acid completely ionizes, all the hydrogen ions will be in solution, making it acidic. And so the anion of it doesn't really affect the acidity of that pH. So an anion that's the conjugate base of a weak acid does increase the pH. Now, when I say increase the pH, I'm referring to numerically the number. So if we have a conjugate base of a weak acid, that means that conjugate base is pretty strong. Remember, it's opposite. So weak acid, strong conjugate base, strong acid, weak conjugate base. A cation that is the conjugate acid of a weak base decreases the pH. So if we have a conjugate acid of a weak base, that means that conjugate acid will be strong. So if it's a strong conjugate acid, then the pH will numerically decrease, meaning become more acidic. Okay, so when we have cations of the strong Arrhenius bases, remember Arrhenius bases said the acids will give off a hydrogen ion in solution and bases will give off a hydroxide ion in solution. But cations of strong Arrhenius bases will not affect the pH. They behave much like the cations of just a strong Lewis acid. Not Lewis acid, Bronsted-Lowry acid. Metal ions will decrease the pH, making it more acidic. And when there's both a weak acid and base, the pH directly is dependent on the Ka and Kb values. So if you have a much higher Kb value on the weak base than you do the Ka value on the weak acid, it's going to be more basic. The pH is going to increase. If you have a higher Ka value and a smaller Kb value, it's going to be more acidic and the pH will decrease. So some of the factors that affect acid strength, we've talked about this a little bit. So remember, if you look here, weak acid, weak acid, weak acid, okay? All of those are weak acids that I've circled. What we see is that they're not weak because their bonds are weak. They're actually weak acids because the bonds are very strong. The bonds are very strong and therefore not a lot of hydrogen ions can go out into solution. If not a lot of hydrogen ions can go into solution, then it's a weak acid. But it is weak because the bonds between the hydrogen and the anion are strong. Okay, so generically speaking, we can say that acidity or the strength of an acid increases as you go left to right and top to bottom. All right, if you think about that and you think about comparing HF, HCl, and HBr, HF is exponentially smaller than, for example, HBr. That's because fluorine is very small and bromine is very large. Fluorine also has a huge electronegativity. It's 4.0 on our chart. So not only are the electrons that fluorine has being held very closely to the nucleus because it's so small, but also it really wants that 8th electron to get that octet, and it will take it from anything and it's going to hang on to it. It doesn't want to get rid of it. HBr is much wider, it's much larger. The electrons are much further out from the nucleus, so they cannot be held as closely together as they are in hydrofluoric acid. So therefore, the HBr will break up pretty easily into its ions, its hydrogen and bromine ions. And what that means is the bond between hydrogen and bromine is pretty weak, so all of the hydrogens can break apart from the bromines and form, completely ionized in solution. Other factors that affect acid strength have to do with the oxyacids. Remember, oxyacids are things like H2SO4, H3PO4. And the reason for this is you have these larger molecules here, and you often have hydroxides, OHs, bonded to some other atom, all right? So the more electronegative whatever the other atom is, the more acidic the atom. So if we have something very electronegative, it's going to be very acidic, okay? And if we look at this here, and we look at these examples, ClOH, BrOH, IOH, HOH, okay? We're looking at decreasing electronegativity, and we're looking at Kas that decrease significantly. Now, all of these are really kind of low. They're very small Kas in general. But clearly we can see that the hypochlorous acid has the highest Ka, and it's going to be the highest acidity. When we look at these polyprotic compounds, what we're looking at is the difference between the first deprotonization, second deprotonization, and after the second and third deprotonization, these are the numbers that we're really going to see as far as them getting weak. So if we were to just look at this and say, okay, I have hypochlorous acid and chlorous acid, and I have chloric and perchloric, you'll notice the differences here have to do with the number of oxygens surrounding the chloride ion. Okay, we go from 1 to 2 to 3 to 4. The more oxygens that are present, the stronger the acid. That's partially the reason H2SO4, with that first deprotonization of the hydrogen, is so strong. So when we look at these, your rule of thumb is that with oxyacids, the increasing number of oxygens surrounding the anion, the stronger the acid. Resonance. Now, there's supposed to be a picture here that's not showing up. I'm not sure why. But if you remember, resonance has to do with where the double bond is. And so, for example, if I'm looking at this, it can also be like this. It can also be like this. And what's actually happening is that within this molecule, the double bond is constantly changing between the different oxygens that are present, for example. Okay, so when we're talking about resonance, we're talking about the movement of double bonds around a central atom. Okay, so if we're talking about carboxylic acids, the conjugate base of a carboxylic acid, remember, carboxylic acid, okay, it's carboxylic acid. The conjugate base, carboxylate, excuse me, it stabilizes the base, okay? So the conjugate acid becomes more acidic. With Lewis acids, let me start over. We started talking about Arrhenius, and Arrhenius acids and bases said acids will put off a hydrogen into solution, and bases will put off a hydroxide into solution. That's great, that's true, but it didn't take into account bases that don't have a hydroxide, for example, NH3. That's when we got into Bronsted-Lowry acids and bases, and we said, okay, Bronsted-Lowry acids will donate a hydrogen, and Bronsted-Lowry bases will accept that hydrogen. With Lewis acids, now what we're talking about is the donation no longer of a hydrogen, but a donation and acceptance of the actual electron pairs, the lone pair of electrons. So Lewis acids accept the electron pair, and the Lewis base will donate the electron pair. So what you're looking at here is NH3. Remember, NH3 looks like this, right? And it's got that lone pair of electrons here. The lone pair of electrons is being donated to BF3. If you remember, BF3 has no lone pairs of electrons. Boron, in this case, is one of those exceptions that it doesn't need the lone pair of electrons to make an octet. It's happy not having an octet. It's just as stable. So in order to form a bond, nitrogen will donate its electron pair to the boron to form that bond between them. So in this case, the electron donor, the electron pair donor is the base, and the electron pair acceptor is the Lewis acid. So when we talk about this, it's important to understand that, yes, Bronsted-Lowry is a great definition for defining or figuring out what's an acid and what's a base. But the reality is anything that can be a Bronsted-Lowry base, remember Bronsted-Lowry bases are the hydrogen acceptors, is a Lewis base. Okay? They're the same. I'm going to say that again. If it could be a Bronsted-Lowry base, meaning it accepts a hydrogen from something else, it is also a Lewis base. Lewis bases, this is important, this last bullet here. Lewis bases can interact with things other than protons. Okay? So Lewis bases are dealing with the lone pairs of electrons, where Bronsted-Lowry is only dealing with hydrogens, protons, okay? So kind of like Arrhenius was great, but you didn't take into account things that didn't have a hydroxide, so then we had to come up with the Bronsted-Lowry definitions. Well, now we're dealing with things that behave as an acid, behave as a base, but don't have hydrogens involved, but there are lone pairs of electrons. So this is your last lecture on the acid base chapter. This is where your test ends. You will have your test next Thursday, a week from today, and be prepared, be ready to go. If you have any questions, feel free to contact me.